hear you. You're muted.
Oh, I'm so sorry. Can you hear me?
I can, yes.
Okay, hi. Thank you so much for joining. So our next talk again is going to be by Richard, and he's going to be talking about AI and innovation. But before I start and before I hand over the virtual stage to Richard, I would just like to introduce you guys to all that he's been doing and like what is it that what Richard's about. So basically, disruptor and innovator, Richard James MacCowan blends nature and technology for revolutionary design, engineering, and innovation. His 15 years of experience in real estate, urban design, and nature inspired innovation inform his unique approach. Through Biomimicry Innovation Lab, he advises clients seeking responsible, sustainable solutions. Driven by sustainability and a desire to challenge norms, Richard pushes boundaries, combining finance, design, and nature inspired expertise. He delivers solutions exceeding environmental targets. His innovative approach and passion have garnered him an international reputation, making him a sought after speaker and thought leader. At the forefront of nature inspired innovation and sustainable solutions, Richard is transforming industries and inspiring a more resilient and regenerative future. Richard, can't wait for you to take this away. The stage is all yours.
Thank you very much. Well, I always hate hearing that back to myself. But you got to write a impactful statement. So let me start off. Hopefully you can all see the screen here. Great. This kind of sums up what we're going to be talking about. This is from one of my mentors. Is that the sooner we stop thinking about biology and start thinking in nature of the problem, the greater then people start understand nature inspired innovation. Is a matter more thinking about the systems. So really what today we're going to be talking about bringing life to innovation. So to give you a bit of a background to my that excellent opening, but I've been interested in kind of complex systems, ecology, biology since growing up. You spend childhoods. Well, we always lived in the countryside or close to water, the coastline. I used to spend quite a lot of my time in the summers up in the west coast of Scotland, learning about the interactions and kind of the contradictions that happen between different animals and plants and different habitats, and when things work well, they work well and brilliantly, but also then what happens when you have a disruption into the system through changing climate, or in the case of a lot of stuff in the west coast of Scotland, the putting in stuff like industrial fish farming and the myriad of knock-on effects from that. And that's kind of kept throughout my different careers of kind of this understanding of the knock-on effects of looking at kind of utopias as an ideal, but then stripping it back and understanding there's always these little relationships and sometimes problems that can't actually be solved. So to delve into nature-inspired innovation, or biomimicry, biomimetics, whatever they're called, they're all synonyms each other. One of the most famous ones that probably nobody's ever really heard of, so to call it famous or infamous, the one that's out there and everybody's using is called the Schmidt trigger. Now, this was developed in the 1930s by a researcher called Otto Schmidt, and he was looking at studying signals, fuzzy signals, analog signals, and how do you convert them into digital. And he did this by studying the signals in the tentacles of squid, and that made rise to the thermionic trigger, which is found in everything from your microwave to your thermostat, your mobile phone, computer, drum machine, cars, everywhere where you're trying to take noisy signals and transfer them into something more stable, ones and zeros. And it kind of really sums up kind of the idea where we're coming from. So that everything, nobody's ever heard of it, but it's there, and almost everything we use in our technology. But another person who you may have not realized who very delved into AI and also biology as well as Alan Turing. Alan Turing was most famous for the creation or the solving of the German Enigma code, and actually developed working at Bletchley Park in the UK with a bunch of people to actually as a code breaker. But as a mathematician and working in physics, he was really interested in biology as well, and understanding the transference between looking at self-organization. And one of his last papers looking at morphogenesis really delved into actually, the growth models of things like bird feathers and shark skin. I'd highly recommend to look at some of the research that's recently come out over the past decade, actually proving what Alan Turing did without using anything more than rudimentary calculations, without supercomputers, actually proving stuff that was actually proven right. So a lot of work actually going all the way back is based on Alan Turing. So where does biomimicry and nature-inspired innovation really come from? So it's been around for thousands and thousands of years, these examples. It's really just in the last 20, 30, maybe 40 years, it's really come to the forefront with the environmental movement, as well as advances in technology and understanding more about the living world, as we're delving more into evolutionary biology and ecology. And as I mentioned, the names, lots of different names. And this is taken from some of our research we did in Nature, the State of Nature-Inspired Innovation. So we looked at different ways that academics and then the press is actually viewed, and especially in academic circles, biomimetic. If you're wanting to delve into more research, you can biomimetic and bioinspiration, different versions of that, nature-inspired biomimicry. And it allows you to really delve in and find a greater understanding than just searching for one name. But what really does it mean? So nature-inspired innovation is the study of biological and ecological forms, functions, processes, and interactions to solve human challenges. It's basically reverse engineering nature and seeing how we can solve problems with it. But from that, you need to understand evolutionary biology and ecology. And this is important as we move forward. So evolutionary biology is the study of living things and their vital processes. Whereas ecology is the study of the relationships between these organisms and their environment. We also need to understand enough about evolution and natural selection. And evolution is the change in characteristics of these populations over successive generations. And natural selection is the survival and the reproduction of these individuals due to differences in the how they interact with the environment. Now, some of these processes you find in nature are intentional, and some of them are not. Evolution, natural selection is unintentional. But we can learn from this by running algorithms. But one of the key things to learn about this is different organisms and species have those phenomena, but there's no rules. There's no overarching rules. We've been searching, scientists, for hundreds and thousands of years, searching for rules of the natural world. Even the laws of physics have been broken. So in nature, there are no rules, only exceptions. But one thing you really need to start doing before you start exploring nature-inspired innovation, especially AI, is understanding the energy use. So if you look at these graphs, these taken from a few years ago by Research University Bath, and looking at how do you compare living systems and human systems. And as you can see in red, we love energy, across the different hierarchies, all the way from the nano level, all the way up to the population scale, infrastructure scale, kilometers. Energy is important. Information is heat beaten out of it, especially at the micro scale, the second column along. Whereas in the natural world, especially up at the larger scale, population scale, information is important. Energy is very hard to get to. So is substance as well. So that's materials, things that make things up. So a lot of things, there's a great research paper called The Survival of the Cheapest, basically saying that nature uses tends towards less energy and less material. So it does things by embedding information, using information to construct instead. And looking at different ways at what time is, the time variables, over the temporal and spatial dynamics. So I look to nature. What's the complexity of it all? It's understanding the relationships. There's a great quote by Peter Bentley, who works in artificial intelligence and machine learning with a focus on biology. And he really sees that it's about the adaptability, adaptation, self-organization, and self-repair. You can see that just by looking at, understanding the self-repair of bones. and then start understanding how evolution and actually building in, looking at parasites, looking at the cellular level, understanding even down at the DNA level of actually how can you actually start understanding detecting fraud detection through this, or looking at complex problems by looking at ants and colonies. There's even ideas of actually looking at music in the future as well, which is actually some of the stuff that's already out there. And we'll skip over that because I've already mentioned this, but this ties into something later. So, because of all this, there's been a vast increase of these areas over time, patents, publications, news articles, and we're seeing a lot of areas of development, materials science, chemistry, biochemistry. But the biggest area we looked from our research is actually in delving into computing, and the two biggest, the biggest areas are AI, machine learning, and nature-inspired computing, with robotics tied in as well. Now, we're not really going to get into robotics today because that could be a whole other fascinating talk, especially looking to Boston Dynamics and all the other things that they're doing with their robots there. Where you start exploring like the relationships between computing and also the industry as well, you start realizing, excuse me, that a lot of the stuff coming out of universities and also research as well is very topical and related to actually what we're doing for the moment. So if you're looking at AI, machine learning for industry 4.2 for manufacturing, creating new materials, building in neuroscience is tied very much into the artificial intelligence. The sensors work with the manufacturing and robotics, tying it all together. So this is tied into how we explored and looked at different industries in the FTSE 100 across, and seeing how the links and relationships between the academics. So let's delve into understanding who's actually learning from nature. So one of the most famous one out there, Google DeepMind. Now, DeepMind started in London. The research center started looking at neuroscience and actually can they delve into the complexities of human brain and use that to solve problems. Now, this opened up a vast treasure trove of complex problems they ended up solving, from simulations, creating algorithms, programs that are able to solve very, very complex game situations out there. And recent developments by DeepMind is their genome project, where actually they have developed around 800 new types of materials, be this metamaterials not found in nature, or delving into biomaterials. It would normally take 800 years, or previous 800 years of solving. They've done this by tapping into large data sets from various universities and other archives around the world. And this allows them to very rapidly create new materials, which is absolutely fascinating and brilliant way to do this, because this is something that's I'll mention later on as well. Now, on the other hand, at the same time when this was launched, researchers at the University of Sheffield in the UK were looking around and saying, well, hold on a second, why do we need to work with neuroscientists to actually map out the human brain? Why don't we look at insects? Specifically stuff like the honeybee with a brain, hundreds of thousands the size of the human brain, and vastly minute levels of neuron differences, but they solve very complex problems, either individually or as collectives. So from this, Opteran Technologies was born. This allows them to create edge computing, work with robotics and drone technology, which allow even event-based vision, which allows for higher, quicker processing, more effective processing carried out using a lot less energy and a lot less equipment needed. And for those of you who work or have been following, the popularity of these large language models and the various other development of processors and computing power, we're using a lot more energy for, one, to create the materials for the data centers, and two, for the processing power as well. And where do you base them? Do you base them in the cooler climates, or do you base them in somewhere underground, or do you use a lot of water and cooling to keep these cool? All of these are obviously very much carbon intensive. So the growth of a lot of these platforms are actually, you're finding, very much linked into kind of issues around climate and carbon emissions and carbon reductions. So what you're now finding with Opteron is they're developing a number of other solutions across this. So looking, smart drones for working in cities, allowing drone technology, especially for out of sight. So a lot of drones, when they're flying around cities, still need to have very clear line of sight towards the user because the amount of information sending back and forth. But with their software built into, you don't need this because they can very, very quickly put this back and forth. So it's getting past some of those very, very micro delays that, although you think, you and I may think is not important, but working with drones, especially around populations, can be very challenging, and safety standards are very, very high. And finally, for case studies, delving into a startup based in Japan called Sakana. And Sakana, what they've been doing is delving into collective intelligence. So they've been looking into swarms of fish, schooling of fish, swarms of insects, murmurations of sparrows, a case with this picture here, and actually looking at how this collective intelligence can work. They're also building these in with evolutionary models as well to allow these algorithms they first created to actually adapt and change. And this is allowing, what they're actually doing is they're looking at ways not only to create solving complex problems by nature-inspired AI, they're looking at how can they bring lots and lots of these different models out there. How can they tap into large open source models, large language models, large data sets, and using these evolutionary algorithms they create to actually interrogate and combine them together to find more effective ways of solving problems. So two ways you can do that: by directing it and almost searching for a goal in mind, or another way, but like evolution is actually unintentional, just set it off and see what it comes up with. Now, again, very much by tapping into what Opteron did and various other companies about using net less energy, it's very much a case of, can they create more optimized systems or fit for purpose that are not using as much computing power? And also, there's also a lot of redundancy built into a lot of these algorithms and programs that can we actually remove this by using nature-inspired algorithms? Because it's the power of tapping into the collective to build something new. Now, if we go back to Alan Turing and the ultimate interpretation game, I really do see, and maybe I'm a bit biased, but more and more companies coming out. You've got the bionic chip coming out from, IBM. DeepMind are moving forward. If you're based in the UK, or I've heard of it, ARIA, which is Advanced Research and Invention Agency, they've currently got a program running called Nature Computes Better. And the main area for this, which is a kind of DARPA-inspired model, is to look at what I've touched on beforehand. We're using huge amounts of energy for computation. Can we look to nature to create new algorithms? But at the same time, can we create new materials for semiconductors as well? So it's the hardware and software that we're looking at the same time. And I do believe that actually by looking into areas around, new materials, new biomaterials, new ways of creating metamaterials, by looking at different composites and based on the way nature constructs, we'd actually be able to find it. Whether that's creating new structures by looking at growth models, say slime mold, looking at how trees interact with the environment, and again, looking at bone growth models. We could even start understanding how soft and hard coral reefs grow and adapt, looking at how can we find ways of resiliency and adaptability for our infrastructure. But one of the really, really key ways here I see is looking forward, is actually tapping into these large amounts of data. Now, the UK's Natural History Museum, in London, is now tapped into a European network where they're digitizing all their collections. And this has got everything going all the way back to Darwin's work, and all the various notebooks on the Beagle. as he was developing the theories for evolution and natural selection, which allows researchers to tap into vast data sets, building knowledge graphs, ontologies, allow you to actually then start exploring this more, to look to new materials. Because one of the biggest challenges, especially in nature-inspired innovation, is where do you find the information? How do you know it's relevant? And some of our partners are actually working on this to build these models by going all the way back to saying, right, everything, majority of life evolved through trade-offs. What are the compromises and the contradictions found between competing things? Like, why is it energy? Why is energy hard to find? Why do you use certain substances here instead of this? How can we turn around and develop new things for the circular economy? Understanding different biological processes for breaking down materials as well, and all that needs an understanding of the different relationships, instead of just isolating, like a lot of things do, isolating a function and taking it out of context. And this is why a lot of these AI machine learning companies and delving into engineering, construction, are all looking at this kind of collective intelligence for problem solving. Because we don't really know where we're going with this. Yeah, we can kind of guess, and you can kind of take a futurist slant on this by looking at what's coming out of universities, who's funding what, where's the ideas coming from science fiction, where do the big companies put in their bets. We've all seen this quote from knocking around for years from Steve Jobs about the intersection between biology and technology. Is that integrated AI? Is that integrated materials? Biodesign, or is it a bit of both as well? I think it might be a bit of both. Now, the reason why I'm showing you this is, so we're currently, there's a lot of research out there, but instead of building algorithms kind of in a top-down process by looking at it from a kind of a godlike status, you're staring down, you're bigger than it. Why not work with the insects, the microbes, the trees, understanding and actually have sensors that actually construct with them? So you're creating a 3D printer, you're creating an algorithm that learns actually what's happening as it goes around, which you can then repeat, because what you're then doing is you're picking up cues from how, say, ants build a nest, a bird builds a nest, termites construct a mound, and you're actually not doing it just from looking at top down, side on. You're actually learning across 4 dimensions and what's happening, what are the feedback loops that are happening, what are the changes that are happening in the environment as well. So you can build all these things about learning from the environment at the same time to actually construct and actually make these an active 3D printer. And this actually really just goes beyond biomimicry, which kind of then taps into kind of this areas which is completely different. And I've not touched on this yet. It's completely biological computing, going down at the cellular level, putting encoding DNA with other type of code that can be passed on, creating computers out of male sperm or things like that as well. And this is all area of fascinating, is could you make it in the future, all our computers kind of going to be biological? Are we going to grow them? If anyone's into science fiction, one area you could think of is the Borg, or the other one, if you remember, from the 1990s into early 2000s, Lex, where the spaceship was an organic spaceship that actually grew. So you can start exploring those kind of ways. And that kind of gets you start thinking, are we delving into a cyber solar techno punk kind of future? So where are we going with this? So I really do think moving forward, we're going to see a symbiotic relationship between these two areas. It's natural. That's not just a pun. As they're looking at more effective ways of computing power and algorithms to solve more complex problems. We're going to see that hopefully with the development, a lot more of these companies that develop this understanding and actually the energy processes and material use as well. And we're going to be finding new ways of doing things that use less of these, because it's not necessarily to make all these high performing systems at times that may only be doing the fraction of it. I'm sure everybody who uses the large language models that are still getting it to write poems, when actually that they're vastly useful for co-pilots, especially if you start building your own one bespoke based on your own information. I do think as we start understanding more and more about complex forms and complexity science, where this is at the city level, collective intelligence of us as groups, and I mean us as groups getting things done well, not parents from football or rugby and WhatsApp groups, because that seems to be collective stupidity at times. But I really see that, more and more we understand, individual phenomena from different species of insects, and flocking birds, and plants, and that we're actually going to be developing new ways of solving problems. So I really like this quote that kind of sums things up. If you want to change the way you make things, change the way you do things. And if you want to make major changes, change the way you see things. And for that, you really need to start thinking of delving into looking into the natural world. So that was kind of a whistle-stop tour of the areas of inspired innovation.
That was actually, I think that is the first time for me, I think that was the first time I actually heard like a topic that was really different, because mostly we cover ethics, we mostly cover the majority of these topics, but this was the first time I heard like biomimicry, and I think that was a really good topic. So thank you so much. Can we have the questions coming in, please? So I think we can open the stage for the Q&A. So if anyone has any questions for Richard, please start populating them in the comments so I can start, we can start the discussion. Anything at all. Richard, anything particularly that you want to touch base again, or anything particularly interesting that you feel should be taken note of when you speak of biomimicry?
I would start looking around. The companies are doing open source models, especially for this. The ones that are developing large language models, because then you can start adapting it to your own needs. I tend to set up little Google alerts or whatever I'm using software to track to look at what's happening with. The key thing with this now, look at what's coming out of the startups and the big companies, because the universities, as soon as they write a grant on this, the grants application's already out of date, because the speed that we're developing things. I think it's absolutely fascinating, and it's not an area I specialize in. I'm more of a generalist, but I'm seeing from a number of our people we've been working with. I mean, I've been delving into creating data silos for like knowledge graphs the past 10 years, and actually seeing something built up enough to solve it. NASA are developing models to find new ways for making materials, which is really interesting as well. You've got a lot of companies looking into a lot of this for, building, more efficiency for construction techniques, designed for chassis of cars.
Yeah.
So it's just a case of finding the right area to actually work in.
I mean, that's I think that makes sense. Okay, so I think our audience may just be feeling a bit shy about asking questions. I'm not sure, but if there are any questions coming your way, rest assured they will be directed towards you. And I think we can end your talk at this note.
Yeah, thank you very much for the invite, and good luck with the rest of the conference.
Thank you so much. Thank you so much for joining, Richard.
Thank you, and I hope that it cools down in your office soon.
See ya.
Thank you. Bye.